That is not my idea. That is not my idea. I did Oh, you're so good.
Oh, I don't know. I'm going to knock on my neighbor's door. I reported Dan It's not big.
Okay, sit down.
I was worried. I was like, are you okay?
Listen, I will teach pump today and Wednesday. Then I will stop for the moment. On Friday, I will teach you about residue curve map. How do you find all the azeotropic relationship, azeotrope, for your project? Especially for Tree Eastman project team. They want you to identify all the potential azeotrope. After that, next week, I return to pump. That's number one. Number two, look at page 301. Specific speed, affinity law. Those are important when you buy a pump or you want to develop your own pump curve. Specific speed we cover on page 295. Let's review it briefly. N, impeller speed. Q, gallon per minute. Head, discharge pressure. Foot. This relationship a little strange. 3/4 power, 1/2 square root. You actually can develop this from dimensional analysis, which we'll do in a minute. Why is the importance of specific speed? Page 297. On the top, you see a plot. Let me enlarge it. value of specific speed smaller than 8,500, you can buy those pumps from vendor. Between 8,500 and 12,000, that requires special order, expensive. Above 12,000, not available. No one will make it for you. Example, impeller speed 1800, pumping rate 2,500 gallons per minute, discharge pressure in terms of foot or liquid 50. Their specific speed is 4,800. You can buy this pump. That is the first thing we talk about, specific speed. Back to page 301. Now, when you talk to vendor or old timer, you say, I only pump for 1750 RPM. Can you give us 2,000 RPM pump curve? The vendor will be laughing at you. He knows you do not know pump.
Can you zoom out, please? It's not very visible.
Okay?
Thank you.
You want, this is available. You want it at 2,000 RPM. You will say, can you create your own pump curve? Do you know affinity law? Okay, go to page 347, give you one example. Available 1750. You want 2,000 RPM. This pump curve is 1750. You have 0.8, 300 gallons per minute, head 160 feet, and brake horsepower 20. How about at 2,000? People will tell you apply so-called affinity law. This is empirical. Let me explain to you where does this law come from. It's not real law, empirical relationship. But pump vendor like to call them law. You see here, pumping rate ratio, head ratio, brake horsepower ratio is proportional to impeller speed, linearly, square, third power. This is good. Those two are approximate. But people call it law. Used anyway by all the vendors. So let's understand what is suction speed, affinity law, from a simple dimensional analysis. Page 301. Power consumption is a function of density, rho, of liquid, impeller speed, and impeller diameter, d. Oh. Oh, dropped it. All right. You write on the dimensional analysis. Did you learn that in fluid mechanics? Okay. Constant C, power A, B, C. You put down a dimension, mass, length, time, A, B, C. You can solve this. Power is proportional to density linearly. Impeller speed, serve power. Diameter, fixed power. Now, linear velocity on the impeller tip, there's an empirical relationship. Linear velocity of liquid U is proportional diameter, impeller speed, conversion unit. That's empirical relationship used by Vendor. So volumetric flow rate Q, this linear velocity pi over 4 diameter square area. You plug in, this gives us pumping rate Q proportional to impeller speed N diameter to the third power. Now, here, and the impeller, you mainly have pressure drop head, kinetic energy. Approximately equal, you plug in this relationship, head proportional to diameter square, N squared. Those two relationships, first, D to the third power, proportional to Q over N, right here. Second, here, H, D squared, N squared. D squared is H over N squared, or D to the third power is proportional to H, 2/3 power, and third power. You have this relationship. So now, from here, D to the third power, you could Q over n. Q over n is proportional to h, 2/3 power, n third power. So, we come up with a relationship. This, you rewrite it, a squared times q over h 2/3 power equal constant. That itself is our specific speed. Specific speed. You can derive it from dimensional analysis. So, on page 303, specific speed, depending on the value, less than 8,500, between 8,500 and 12,000, above 12,000, it determines whether you can buy the pump. So now, with the relationship we got, Q and D to the third power, H, P. Okay? So let's go to the next page. This is the exact relationship from dimensional analysis. What if D1 equal D2? Constant impeller diameter, you drop the second term. Q1 over Q2, N1 over N2, H1 over H2 squared. And this constant, third power. So this is exact relationship. When D1 equal D2. Now, what if for small changes in impeller diameter, now Q1 over Q2, people like to have a relationship 1, 2, 3. So I don't want the 3. I put a 1 here. 2 stay. 5, I don't like it. I put a 3. So Q1 over Q2. Okay? When the impeller speed R equal, you drop that term, you drop the term, you drop term. First one, you force the third power into linear relationship. Second one, stay. Third one, fifth power, you force that to be 3. You call this affinity law. That is approximate, not exact. So whether if your D1 equal D2, you can use this relationship. If your N1 equal N2, this suggests you use this approximate relationship. 3 become 1, 2 stay, 5th become 3. That is affinity law. And this is how we apply that on page 347. So, next time, you have D1 equal D2, same impeller diameter. Your pump curve is 1750 RPM. No, gallon per minute. No. This one. Diameter. Okay, let's look at the page. Yeah. So, let's apply this. Given condition, point A, on the pump curve, this is 1750 RPM. Now you want to change to 2000 RPM. Because the vendor cannot provide you. They want you to do it yourself. What do? 1750 RPM versus 2000 RPM. Linear, square, third power. Pumping rate, Q1, Q2. Head, H1, H2, brake horsepower, BHP1, BHP2. You calculate this, that will be the new operating point at 2000 RPM. That is called affinity law. Okay? Now, let's see. Let's just see one page. In the beginning, former student, he went to Flowserve. That is the largest pump vendor in the world. In Maryland, they have an office. Job interview. The question they asked him, affinity law. Okay? They were surprised. How come this undergraduate knows affinity law? After he answered that question, he got a job right on the spot. Okay? You have different operating conditions. You do not have pump curve. How do you find a new performance parameter? Affinity law. Okay? Now, here comes the important subject now. We move on. Page 308. hydrodynamic characteristic of centrifugal pump. Our goal is the following. Look at the pump curve. Understand capacity, total dynamic head, brake horsepower, net positive suction head available.
Excuse me, what page is this? What page is this?
What?
What page? Page, what page?
354.
Thank you.
354. Impeller diameter, pump efficiency. So we'll go to one by one. Make sure you know how to get them. What are the important things you need to pay attention to? You are pumping a liquid. When you did a 1998 project, several teams were anxious. They start jumping on that. Read the article on the size of pump. You do not have sufficient information to do that yet. First question I ask you here, this is 350 gallon per minute. Is that for water or for some other liquid?
Water.
For pump curve. Pumping rate. If you have a viscous liquid, 100 centipoise, pumping at 350 gallon per minute, do you reach 350? Shaking his head, you cannot read it. You must do viscosity correction. So now, the first question is, you did your 1998 project, liquid. What are the two most important properties you need before you continue to do pump sizing? Your boss asks you to size a pump. What are the two things you're asking for?
Volumetric.
If you don't have it, you cannot do it.
Volumetric flow rate and differential head.
He gave you 300 gallons per minute. What else you need to ask?
Differential head.
Two things. Otherwise, you cannot continue. Two things.
Specific gravity?
What?
Specific gravity?
No.
Differential head?
No. I'm talking about physical property of liquid being pumped.
Velocity?
Now, this is an important question. Your boss asks you to size a pump. 300 gallons per minute. You immediately asking two questions. Otherwise, you cannot continue your work. Okay, that's quiet. 308. Let's start. Pumping temperature. Pumping temperature. Why do you need pumping temperature? That will give you vapor pressure. vapor pressure. Just one. Why do you need vapor pressure?
Cavitation.
Yeah, good thinking. Later on, when you find nerve pulses suction head available compared to nerve pulses suction head required, you need vapor pressure. So, vapor pressure determined by pumping temperature. What is the other physical property do you need? Otherwise, boss, I cannot do it.
Boiling point?
Viscosity. If you have greater than 100 centipoise, you have viscosity correction. 300 gallons per minute might become 310 gallons per minute. We have some correction chart for you to change. So, if somebody asks you to size a pump, don't accept the job so quickly. Okay? Can you tell me the pumping temperature? What is the viscosity of your liquid? Okay? Capacity, gallon per minute. Pumping temperature, viscosity. That's what you need before you read the pump curve. On this pump curve, it's simply this line. Okay? If you have viscous liquid, we're going to have some correction. You find a new pumping rate. You can see this. I give you this book, Pump Engineering Manual. Okay? You won't find from a viscous flow rate, what is equivalent water flow rate on the pump curve? We're going to learn this, okay? All right. Total dynamic head. This is the most tedious part of pump sizing. First, static head. Look at page 310. Head in feet. The pressure in PSI times 2.31 divided by specific gravity. You look at the three pumping system. Here, the calculated discharge pressure are different. different. But you look at suction tank, central line on the pump. This elevation here, this elevation here, elevation. Head in feet. How many feet of liquid static head? This side, they're all equal, all equal. But you're pumping 3 different liquid, specific gravity different. That's why the discharge pressure is different. Discharge pressure different. Specific gravity different. But elevation remain the same. Okay, now keep going. Page 313. We have 2 types of system. The surface of suction tank is below central line of the pump. Discharge tank above central line of the pump. In terms of potential energy difference, total steady head is the sum of the 2. This is called suction lift. Now, here's suction tank. Here is discharge tank. The elevation difference is this minus that. Okay? So, remember central line of the pump determine the total potential energy difference. Okay? Total dynamic head, potential energy difference, raised liquid level. Provide liquid velocity inside the piping. Now, suction pipe diameter, discharge pipe diameter, they may be different. Okay? For constant volumetric flow rate, linear velocity in the discharge pipe, suction pipe may be different. You need to provide liquid velocity. That is the kinetic energy difference. The third one, overcome frictional head law inside piping, plus through expansion, contraction, control valve, etc. This is the most tedious step. You don't want to do it. Pump against pressure. That is pressure energy difference. In this is 1 bar. This is 2 bar. You want to push liquid from lower pressure to higher pressure. You need to provide energy. So, now, keep going. Page 14. Velocity head. You have section pi ID. Four pi ID squared, that's area, right? Section side linear velocity, this is your gallon per minute. Velocity head, Vs squared over 2g, with d squared over 2g, discharge section. Now, in many applications, is Vs or Vd less more than 10 foot per second. Vs squared 2g is 10 squared over 232.2. This is about 1.3 to 1.4.
Shift it a little bit, please. Thank you.
Normally, if the velocity less than 10 foot per second, you may ignore this term, but not always, depending on problem. We have detailed numerical example for this step later. This step, frictional head loss in a suction pipe, in a discharge pipe. H suction, friction. H discharge, friction. How do you calculate that? 315. First, in your fluid mechanics, you have a Darcy friction factor, frictional head loss, a Darcy friction factor, length of pipe, diameter of pipe, V squared over 2g. Why do you see Darcy friction factor? Page 317. Friction factor Darcy friction factor Reynolds number for laminar flow. This (64) divided by Reynolds number. Okay, 64 divided by Reynolds number. If you have a higher Reynolds number, the different curve. In my Excel spreadsheet I gave you, in the Crane technical manual, there are more clear picture. Now, the other, so Darcy friction factor is friction head loss, left hand side, divided by L over D V over square. Is functional Reynolds number, roughness, epsilon divided by D. Page 316. Epsilon divided by D. Roughness of pipe. Okay? And this pipe diameter. The more clear graph for you. Now, people sometimes use the fanning friction factor. What is the difference? L over D, V squared over 2G. Here, you have a 2 here. There's no 2. So it's 1/4 of Darcy friction factor. So, to summarize, friction head loss, friction factor 2 L over D V squared over G. Darcy friction factor, there's no 2 here, and there's the 2 here, so a difference of 4. Laminar flow, Darcy friction factor is 64 divided by Reynolds number. Turbulent flow. Now people have different kind of correlation. 315, 316. This Stu Churchill, University of Pennsylvania, former AICG president, he liked to do correlation. He gave you a Darcy friction factor correlated with Reynolds number, constant A and B. A involves Reynolds number, roughness. B, Reynolds number. This is for all laminar turbulent flow. Claimed to be the best to use. Okay, so laminar turbulent roughness. You're falling asleep, I know. I fall asleep about this too. Tedious. The part of some pump sizing, you hate it. Okay? But to cite real pump, once you have elevation, pump location, everything else, you need to do calculation, okay? For your 1998 design competition, you didn't have sufficient information.
It's 2:15.
Oh, time is up. Let's continue on Wednesday. Key need viscosity and pumping temperature